Thanks for the invitation and apologies in advance for an extremely dry talk. I mean, it will be probably the first talk of the day without any picture. But I will do some proofs and I'll try to go slow and gently. So this is joint work. So it has been published in Neurips last year with Evgenii, who's sitting here, Christophe Giraud. So the three of us are with the math department in Orsay, and Zhen Li, he's working at BNP Paribas full-time in some finance department, etc., and doing the PhD on weekends. So it's pretty impressive. It will take some years. I mean, it's expected to last rather 5 years, 6 years, etc. So it's not as if he could do it full-time, but we're making slow progress. Okay, so that being said, I first want to, so actually, the Neurips article is there. I mean, it's, oops, yeah, it's the final slides, but I'll try to spend most of the time on the basics. So the basics, the most basic case is the k-armed bandit setting. So you have some model. So in statistics, we call model what you know about the distributions. So take as example, our running example later will be all probability distribution on the 0-1 interval. Okay, so that's a simple model. So you have some model, you have k arms, and each arm is associated with an, of course, unknown probability distribution. So we have nu1, nu2, till nu_k. And at each round, you can pull one of these arms and you will get some reward, just like in the casino. Okay, you put a coin, you imagine that the slot machine has several arms, you pick an arm and you try to identify which arms provides the best rewards. And of course, this arm you want to pull it more often. But you have no clue in the beginning, so you have also to explore. So you'll explore some arms, but at some point you'll identify that some arms are better, so you'll use them more, etc. So there will be what we call a trade-off between exploration, you have to pull arms so as to get information, and exploitation of that information. Okay, so these are the keywords in Bandit: exploration, exploitation. Okay, notation. So new for the, yeah, I'd realized that this one was a tough pointer. So new for the distribution, mu for the expectations. So at each round, the statisticians picks an arm AT. So the k into brackets means the interval 1, 2 till k. So statistician picks an arm based on the past information. She gets a reward y sub t drawn according to the a sub t distribution. So in Bandit theory, we use the female for the statistician, and usually the environment is the male. Okay, so she gets a reward drawn independently according to to the distribution she picked, and that's the only feedback she gets. And then we do it again. Okay, and there's a tension between estimating the distributions, actually the expectations of the distributions, because we'll only work in expectation, versus getting rewards. So to phrase our goal, so our goal is to maximize rewards, but that's usually phrased in minimizing regret. So it's been decades that regret has been minimized in the machine learning community, but I remember in my good old times in the early 2000s, we were not too many minimizing regrets, and it was always a pleasure discussing with PhD colleagues and telling them, yes, I'm minimizing regrets. And also when I was having dinner in town, etc., you say you minimize regret, or people do say, wow, that looks fancy and enjoyable, indeed. So you want to maximize your cumulative payoff here. So instead of maximizing this, we'll be minimizing something else. So your best choice, had you some God knowledge, you would know the best arm. So you would always pull that arm, and on average, you will get t times max of the mu sub a. So the max of the mu sub A we denote by mu star. So in expectation, you'll get T times mu star. That's the best God would do in expectation. Okay, so that's our goal, and we're comparing that to what we actually got, the sum of the payoffs, and we're taking expectations for simplicity to start. Okay, so that's what we call regret. So on the next slide, it will be our first proof. I'll show you that we can rewrite the regret in the following way. So I'll denote by n sub at the number of times we pulled arm A, and I'll show you that the regret can be decomposed as the expectation gaps, mu star minus the expectation of an arm, times the expected number of times you pull that arm A, which indicates that in all bandit proofs, to minimize or to control the regret, either with upper bounds or lower bounds, it is sufficient and necessary to control the expected numbers of time you pull each suboptimal arms. Okay? So, if setting is fine, first proof. So on many slides, I'll just summarize the notation of the earlier slides above. So you see we have k distributions with k expectations, and at each round we pick an arm, and we get and observe a payoff independently drawn according to the distribution we picked. Okay, and we'll rewrite the regret. So the first step is what we call the Tower rule. Tower rule is expectation of the conditional expectations is an expectation. Okay, so let's see the conditional expectation, our payoff. Actually, by definition, since once our arm is set, the payoff is independently drawn according to the distribution new index AT. So that payoff has expectation mu index AT just by definition. So that's the conditional expectation, and then I'm taking expectation on both sides, and it shows by the Tower rule that the expectation of my payoff is the expectation of mu sub AT. Okay, and I'm substituting this in the definition of the regret. So the regret is I'm just writing it as a sum of mu star minus expectation of the y's. Okay, so I'm just inverting the sum and the summations. I'm replacing expectation of yt by what I just showed. And now I'll be decomposing according to A. Okay, so I'm just adding here, if you wish, sum over A, mu A, indicator that capital A sub t equals I. Okay, so I'm just doing this. And then I'm inverting the two summations. So I'm first summing over I, and then I'm grouping all summations over t. And this is where the number of times I played A appears. Okay, so we have the rewriting of the regret as the sum of the expectation gaps times expected number of times we played a given arm. Okay, so that was the first proof. I hope you survived it. And now I'll show the most popular strategy. Okay, if there was a 101 bandit course, that you would see that in the first hour. So we'll take the model of all distribution over the 0-1 interval for simplicity. And so the strategy was introduced, well, actually analyzed by Peter Owen, Niccolò Cesar Bianchi, and Peter Fischer in 2002. If you discuss with Niccolò, he would tell you that the strategy was known. It's just that they provided the finite time analysis via the Höffding-Azuma inequality. And Niccolò is always so surprised that this paper is so much cited, but of course the paper is cited. Whenever you write a bandit strategy, you have some optimistic way of thinking, you have some upper confidence bounds, and you cite that paper. Okay, so the strategy is as follows. In the first K rounds, I didn't write it, but you pull each arm once. Okay, then you have some empirical mean for each of the arm. You shouldn't trust these empirical means. I mean, there are traps. If you trusted these empirical means, and always played the arm that got the best reward, of course, there would be a large probability that you didn't get luck and identified a bad arm, which is why we want to continue exploring all arms. And this is quantified in the following manner. For each arm, we'll maintain what we call an index, which is not given by the empirical mean, but by the empirical mean plus a confidence bonus. Okay, so empirical mean mu hat, confidence bonus, what is in the root. Okay, and this, as we'll show next, will be an upper confidence bound on the true expectation. So with high probability, that guy is, upper bounds the expectation. And we'll be looking for the bright side of the world. We'll be looking, that's an optimistic way of seeing life in bandits. We'll focus on the upper confidence bounds. And we'll pick the arm for the next round that is associated with the current best upper confidence bound. Okay, so you see in that term that the arms that were not pulled often, for these terms, the confidence bonus will be large. So that helps continuing exploring. What we'll show next, proof number 2 and proof number 3, are these two regret bounds. So the first one is called a distribution-dependent bound. Why? Because it is of the form a constant that depends on the underlying distributions times some rate, here a log t. The second one is called the distribution-free bound. It actually corresponds to a worst case. We'll be taking the soup of the regret over all possible k tuples of distribution in 0, 1. Okay, so these bounds have really different natures and merits, etc. The first one looks nice because it's log. Everybody would prefer a log over a root. The slight difficulty in the first one is that the constant can be arbitrarily large. Okay, the expectations gaps are small. As they become smaller, the constant blows up. Okay, which is not the case in the second one, but of course the rate is not as good in the second one. Okay, different merits. The two bounds are nice and they are suboptimal. Written this way, the distribution-dependent bound can be made sharper in the first case, and the log t is unnecessary in the other case. But what I like in those bounds is that it's easy to prove them, and the second bound will follow from the first one. Okay, so I'm ready to trade off a log t for pedagogy, and I'm sure you don't mind. Okay, so proof of the first bound. So the key really is the Evgenii-Chzhen inequality. Oops. Well, I'm just giving up. So Evgenii-Chzhen inequality, you typically see it for IAD data. If you have n IAD copies of some 0, 1 bounding variable, then the average over those n copies compared to the true expectations is let me write it here. So say that this is an average of ID copies. Okay, so the Evgenii-Chzhen would tell you that the difference between these two would be with probability at least 1 minus delta, like something like this, with constants, probably a 2 here, something. Well, yeah, and 2 here. Yeah, something like that. Okay, but this is when you have a deterministic number of terms. It actually turns out that we use that as a building block to prove this inequality here, just by adding some decomposition depending on the values of NAT. And we take also delta equals t to the minus 4, something like that. Okay, so because we do that decomposition according to the values of NAT, it adds some t factor. Okay, otherwise we would have a t to the minus 4 here, but because of decomposition, it's only a t to the minus 3. Okay, I don't want to give too much detail on that. It relies on theorem norm-Doubs optional sampling. Okay, so but just the idea is that we leverage this just by controlling the fact that n is random. Okay, but I'm putting some dust under the carpet so that the proof looks simple. Okay, now our goal. Remember that our goal is to control the expected number of times we pull suboptimal arms. So I take a suboptimal arm, I call it B, and if it's not an optimal arm, then in particular, the index associated with B is larger than the index associated with an optimal arm. Okay, so we have that first inequality. Okay, and now I'll be lower bound. So I just assume that this inequality holds for all A's. So with high probability, it holds for A star. So I can lower bound the index for A star by the true expectation of A star. And I can upper bound the empirical average of B by the true expectation plus the root. Okay, so here it's larger than mu star, and here it's smaller than mu b plus another root, and I already had a root, hence that factor 2. Okay, so if all goes well, and it goes well with high probability, I have that ranking. So, and that deterministically imposes that NB, the number of times I pulled the suboptimal arm B so far is not too large, that it's something of the order of a log. Okay, a log small t, but I upper bounded the small t by a capital T. Okay, so if all goes well, the number of times B was pulled is bound to be smaller than that. Okay, and since I'm taking an expected bound, I can sum up all the probabilities of these small events. And yeah, they are the order of t to the minus 3, so it sums well to a constant, etc. You don't even see it in the regret part. Okay, so which is why this gives you exactly the main order of magnitude of the regret part. Okay, so that's the first proof. So you sum and you obtain the bound above, which will substitute to get the distribution free bound. I mean, it's Rémi Munoz who showed me in 2008 how the distribution free bound that I'll show next follows from this distribution dependent bound. And I remember I was just amazed by the simplicity and the beauty of the proof. I mean, it took me years to digest it. Okay, so I just show you what we proved so far. We proved this bound. Okay? And the regret equals this times expectation of NAT. So, and I'm writing it as a product of roots. So when I only need to consider the A's that are suboptimal. For the A's that are optimal, I mean, the expectation gaps are 0, so they disappear from the equations. And so when A is suboptimal, I can substitute that bound. Okay, so I'm getting that 8 log t because the denominator is just, cancels out with this term. So it's root of 8 log t times the sum of these roots. And now I'm using the fact that the root is concave. So to get that it's smaller than the root of k times the sum, and the sum of the NITs is smaller than t. Okay, which is how I get the last step. I mean, last step is just Jensen's inequality. So you see, two line long proof. Okay, so this is what I wanted to say for the simplest model. So everything is on that slide. But the simple model, as the name indicates, is simple. So we want to make it more complex. So for what I want to do at the very, very, very end, I need context. So contextual bandits will be that at each round, you're not facing exactly the same bandit problem. I mean, the bandit problem will evolve over time, but you'll get some contextual information about it. So how does it go? So at each round, a context, a d-vector valued context is determined by the environment, either drawn at random or even picked adversarially by the environment. The statistician still picks an arm, still gets a reward, but the question is, which is the distribution of the reward? So for now, I'll just call R of xt.at its conditional expectation. And later you'll see that we'll make structural assumptions on that for the learning problem to be tractable. I mean, we'll need assumptions. Otherwise, if the dependency is arbitrary, there's nothing you can do. I mean, you need something to be learned. And of course, as before, the reward is the only feedback she receives. And the game, I mean, the goal will still be the same. I mean, maximize the expected cumulative payoffs, which we rewrite as minimizing some expected regret. But the question will be, which targets should we pick now? Okay, so I'll define that on the next slide. And I'll now explain the, some handy assumptions. So the simplest assumption would be that there's some linear approximation. I mean, usually people are happy when it's linear, and there are often good reasons for believing that some phenomenon is approximately linear. So how do we do? So we suppose, this is not the way, if you take some linear bandit paper, it will not be written this way. It will be written in different ways, but that, I think, is nicer to understand. So you have some, everything will be governed by some parameter, theta star, so that we will learn that parameter. And then there are transfer functions, and you assume that the conditional expectations are linear modulo these transfer functions in the parameter theta star. So for instance, the case before would correspond to phi xa being some unit vectors in the basis. Okay, and then you only need to learn one of the components of theta star. Okay, it's as if the components of the theta star were given by the expectation mu a in the previous set. Okay, so it's one way of generalizing the previous setting. Okay, transfer functions are known, but parameters are unknown. Okay, and then in that case, we could say that the targets are given by this. So at each round, you compare yourself to the best arm given the context, to the best expected arm given the context. Okay? So, small recap, as usual. So we have context, we pick arms, we get rewards. So the rewards have conditional distribution. Yeah, giving up. So they have a conditional distribution phi in a product with theta star, and that's our regret. And so we want to learn theta star. So by the way, I long wondered what distinguishes machine learning from statistics, and why learning would be different from estimation. Okay, so one answer could be that learning is estimating while it's not the primary goal. So here will be estimated theta star while taking actions, while playing. Okay. So the standard strategy. So I only wrote one reference, but there are two earlier references from 2010 who introduced the strategy but did not analyze it well. And I'm only citing the ones that analyzed it well because I'm a mathematician and I care about analysis and not so much about the algorithms. Okay, so it's called LinUCB for linear UCB. Okay, so it's based on the same upper confidence bound ID, but you hear that there's some linear algebra involved, and that's exactly it. Okay, so the intuition is there. Let's look at this quantity, just for the sake of looking at this quantity, by martingale properties like Evgenii-Chzhen. We can show that it's close to this quantity. Here I'm just replacing y sub s by its conditional expectation. Okay, so by Evgenii-Chzhen, if the phi's were, for instance, bounded, this is true up to a root t. Okay, so if we believed it was an equality, how would we get theta star? So theta star would be this matrix inversed, well, if it has some inverse times this. Okay, and this is exactly how the strategy will proceed. So to make sure that the matrix is invertible, we're just taking some regularization parameter lambda, and we'll be adding lambda identity to that symmetric matrix. So now it's a symmetric definitive positive matrix, and it has an inverse. So I'm calling it m sub t minus 1, and I'm defining theta hat as mt minus 1 inverted times the quantity ahead. So the good thing in theta hat is that I can compute it. Okay, I know the context, I know my actions, I know my rewards, and phi is also known. So okay, this is indeed an estimator. And it's only based on what I played. Okay, so I'm really learning theta. Okay, so I'm just putting again the setting and how we'll estimate theta hat. And in the analysis of LinUCB, so the key will be that there is some confidence region on theta star. Okay, so the key is this. Okay, so this theorem, and I'm not showing the proof. I still don't have a proof that I would be able to present in some graduate course. Okay, one day. I love to simplify proof, etc., but this proof really looks like not mathematic, but magic. I mean, there's some mixture of martingales. You wonder why they take it, etc. I still don't have a good intuition for it. But well, it says that in some Euclidean norm governed by that matrix m sub t minus 1, theta star is root log t close to theta hat, okay, with large probability. And once you have this, the good thing is that you have simultaneous confidence intervals on all conditional payoffs. Okay, so you have one confidence region, and then you have lots of confidence intervals on the quantities of interest. So the conditional expectation of y of when you play arm A is here, and we have so this point estimate. And if you want to see how good it is, so first you apply the Cauchy-Schwarz inequality. Okay, so that term, I mean, you just substitute that bound, and that term I just copied, and this is what we call epsilon, and then that's a three-line long proof that I understand of linear algebra. You can actually show that those the sum of those confidence bonuses, they sum up to something of the order of root t. Okay, but yeah, it's a good example of a proof that mixes probabilistic arguments and linear algebra arguments. Okay, I'm just giving you a flavor, but one of my aims next year is to write a textbook giving a probabilistic introduction to stochastic bandits with all these martingale theorems. So I hope to be able to find a proof that with some natural flow that I could present. Okay, but yeah, ask me again in 1 year if you want a readable proof. Okay, so once we have this tool, then it's easy to imagine what the algorithm could be. So the algorithm is take the point estimate, take the upper the upper confidence margin, add the two, that's an optimistic estimate on the conditional expectation, and play the arm that maximizes this. Okay, so it's same logic, and you can prove a root T regret bound. So actually, I'd started with some expectation, we lost the expectation, and now I'm giving you a high probability bound, but there's a catch. Okay, if you want that high probability bound, then you need to set the confidence level and the delta, 1 minus delta, and the algorithm would depend on delta. Or you can have an expected bound, and in this case, the algorithm does not depend on the confidence level delta. Okay, and same for the first vanilla case at the very beginning, but I didn't want to dig into this at that stage. Okay, so to summarize, we had context, and that was one way of making some structural assumption. Another way, slightly more recent, from 2020, by people from Criteo. Okay, they try to place ads. So that setting will look natural. I mean, in that setting, so let me describe the thing, then I'll comment. So a context is determined, statistician picks arm, so far so good, it's the same. Then an outcome, binary, is drawn with some probability that depends on the context and on the action picked. That's the only feedback the statistician receives, and then she gets some reward that is given by some known reward based on the action and the context times that YT, which we call a conversion. Actually, you're looking whether that a conversion of a client, whether the client or not clicks on the ad or buys the product. This is why you have that random binary variable. But all other parameters are known. You know your margin if the client buys, etc., etc. But the conversion is unknown. Okay, and then they do some structural assumption based on some logistic model. So they take the logistic regression function, and then in the middle you have something linear, I mean with the same form as before. Okay, and then they extend the lean UCB theory to this. So it's more involved because to estimate the parameter here, you need to resort to some maximal likelihood estimation, and it's a true challenge to have all theorems and good theoretical guarantees extend to that case. Okay, but I don't want to detail. And okay, in the not even 10 minutes that are left, and I'm happy because I didn't want to dig too much time on that last part. Well, Evgenii told to me some days ago, oh, I was surprised that you picked that article. It's super complicated to do a talk about it. And indeed. So I mostly want to explain how we came to this. So I'll explain actually the application on the next slide. It's a fairness issue. But first, let me give you the setting. So the setting is that you have context, you pick arms, but now on top of getting rewards, you also suffer some costs. And so I have conditional expectation function for the rewards and conditional expectation function for costs. And your feedback is your reward and also your cost vector. And you want to maximize your payoffs while suffering some hard constraints on the cost. So the cost really cannot go beyond T times some vector valued budget B, okay, which is known, and rewards are what they are. Okay, and so R is unknown, C is unknown, the distribution Q for the context. Well, suddenly for the context, we're not super satisfied with that, but we need them to be drawn ID. Okay, we're not smart enough to work with context determined or picked by the environment. Okay, and of course, we'll issue structural assumptions on R and C. But let me explain where this comes from. So that setting is called CBWK, that's our nickname, Contextual Bandit with knapsacks. Well, they call the various budget constraints knapsacks. I don't really know why. So there's a first reference in 2014, and then the state of the art was that the total budget should be at least of the order of t to the 3/4. Okay, so B can actually depend on t. And that was extremely inconvenient for us because of the application we had in mind. So the application was already stated in a paper from 2021. Well, actually, we had the same ID 1 year after, but you know, that happens all the time. Okay, so we had the same exact idea of using contextual bandit with knapsack to deal with fairness, except that we could provide regret bounds. And to do that, we had to suffer a lot, because basically, as I'll explain, we'll need TB to be of the order of root T. So the math brute force will be in that, from going to T to the 3/4 as a constraint to root T. Okay, and in that article, they were just mentioning that it would be interesting, but they were not providing a solution. So the example is that it's about some fair budget spending among groups. So they were lawyers, and they were studying how to provide rideshare assistance for people to appear in courts. Okay, so if you have some budget, and of course it was a US example, so budget was split between ethnic communities. The question was, should you spend, how should you spend your budget between Blacks, Asians, and Caucasians to maximize efficiency, so appearance in courts, but somehow in all groups, and not unfavoring too much some other groups, while ensuring that overall it's efficient. Okay, so I'm not giving all the details, but it's something that we could translate into equations as follows. So for each guy, you have you decide or not whether you provide rideshare assistance, and there are various levels. So there are various costs. So you have a total budget on the rideshare assistance, and you want to make sure, I mean, the fairness constraint is here. We want to make sure that the average budget spent for one ethnic group is close to the average budget overall. Okay, and we have some threshold margin of error tau between the groups, the tolerance factor, and ideally you want it to be 1/root T, because these are the natural variations that are dictated by central limit theorems. So it's impossible to have 0. I mean, because of central limit theorem, you have at least 1/root T, but we don't want more. We really want to shoot for the minimal, to what is the fairest possible. Okay, so you can translate these two lines into 2G plus 1 cost vectors. Okay, with a B total cost component, and then components that are plus or minus gamma G, where the proportion of people in each group G times tau. Okay, I'm not giving the details. I mean, at this stage, everybody wants to have a coffee break, and I just want to give you the idea. Okay, so the benchmark here is some static policy. So if you know all the parameters, what could you do best in expectation? So in expectation, the policy would be maximizing rewards while making sure that the costs are on average smaller than B. Okay, so that's your benchmark, and the regret is T times that benchmark minus what you get. Okay, with these hard constraints. Okay, so yeah, that's here rewriting, I mean, here we're trying to give the ID of the algorithm. So that's that target. It's a constrained soup. So I'm introducing some Lagrangian. So I'm rewriting it as a soup inf, and then I'm inverting the soup and the inf under some conditions. And then it's easy to see what the best strategy is. It's just a pointwise maximization, okay? So you rewrite the target as this, and this tells you exactly what the ideal strategy was. If you knew lambda star, but it's parametric, which is great because learning parametric parameters, that we can do. If you knew the best lambda, and you had, and since we will have access to the context, we would just pick the A that maximizes this. Okay, and that's exactly what we'll do. Okay, so it's like a direct, I mean, the strategies that were in the literature were a bit more indirect, but here is something super direct. Okay, so that's, yeah, I will not comment the algorithm details, but the idea is that we maintain estimates. So an upper confidence estimate for the reward function, and of course, lower confidence estimate for the costs. So we're pessimistic for rewards, and we're also pessimistic when it comes to costs, but that means lower bounding the costs. Okay, and we take some margin on the budget. Okay, so we do some primal optimization. We play the arm that optimizes this. Then we make some gradient step to learn the lambda, and we go on, okay? And the key, but really I don't want to explain, is that we tune the gradient step in a much better way via, I'll not read that side, but the key is here. I mean, we use some doubling trick. So we start with some initial value of the step size, and if then we have some various conditions to be checked, etc. And if conditions are broken, we're just doubling that value. And at some point, it's automatically of the good size, and everything is fine, etc. And at the end of the day, we get a root T regret times that factor, which is also the factor that the literature had. And we are able to do this under the only condition is that the B is of order T to the minus 1/2 instead of minus 1/4. Okay, so we were very happy about that. It turns out that the meta reviewer of Neurips was also excited by that, which we don't see every day. But yeah, I have to admit that this is like a super technical contributions that even I had difficulties to rig again 1 year after. So I really don't want to give the details, and let's rather go to the coffee break. Thanks for your attention.
Are there any questions?
So each time in the strategy there is an optimistic factor. So I guess it's to take into account the exploratory parts. But if your big T is finite and you know, so you will end the experiment at some point and you know when, I guess at the end you should not explore, you should just pick the best solution. So is there some study about that?
No, actually, I mean, whether T is known or unknown, it's the same. I mean, if the end time would be known, I think I could put a capital T in the numerator here. But it wouldn't change drastically the strategy, and we should continue exploring. I mean, whatever the time spent, there's always a small probability that if you just stick to an arm for the rest of the time, you do it. I mean, you pick the wrong arm with a small positive probability, and the regret would be linear.
Yes.
Okay, which is why we really continue exploring till the end of time.
Okay.
Usually, with fairness constraints, you can really manage the rate. And here it seems that's not the case, but you have lower bounds for the problem you're considering?
No. So, no, we don't have lower bounds. It's just, I mean, the final bound we get here is just the bound that everybody is getting. Okay, so we were happy with that. Note that if, I mean, this is small, then, I mean, you're paying a root t here as well. So, I mean, it all depends on how this varies with B, the opt. So it's, I mean, actually, even the rates are difficult to read in the bounds. I have to admit, and no one does lower bounds in that. I mean, at least not the nice lower bounds like in Lion Robbins in the simplest case, etc. I mean, yeah, it's really terra incognita, the lower bounds. But you're right. As a statistician, we should do lower bounds.
One last question. The proof from problem dependent to problem independent, is it written something? Like in the books, it's always different proof, no? Like this that you did with square roots of expectations. In the books, it's really different proof.
Really?
Yeah, they usually split it by gaps. The sum you split by gaps. You treat one and treat the other, and then find the best solution.
That's right. That's maybe the way Rémi showed it to me, but at least next year it will be written.
All right. No more questions. Let's make the pause, and we're coming back at 4:30.